Here we have a package of pre-response questions that come in a practice exam. And what I like about this particular practice exam, it comes with a huge list of topics that are going to be covered. So that's what I like about this. Not say one-stop shopping, problem solving, but here's what's involved. We've got projectile motion, graph representation, motion graphs, relative velocity, variable force, KV problem, set up but do not solve the differential equation, then solve it. We have rotational dynamics, a yo-yo. We have a mass unwinding from a string, falling. So it's going to represent both translational and rotational motion. We've got energy, system of masses involving friction. So we've got, in this case, 3 masses connected by a cord and a pulleys involved. So we have to treat the 3 masses as a system. Later, the problem is modified to be an experimental design. So experimental design followed by some data analysis. So let's get started. The first problem involves projectile motion. So a projectile is going to be launched at a trajectory theta above the horizontal and on a cart that will be movable right now, but the cart's stationary. So I'm going to read the problem nonetheless. A projectile is launched from the back of a cart of mass m that is held at rest, as shown above. At time t equals 0, the projectile leaves the cart with speed v naught at an angle theta above the horizontal. Projectile lands at point P. Assume that the starting height of the projectile above the ground is negligible compared to the maximum height reached by the projectile and the horizontal distance traveled. So I'm going to take the initial and final height to be the same, and that does simplify the problem. All right, part A, derive an expression for the time t sub p at which the projectile reaches point P. Express your answers in terms of v naught, theta, and the physical constants as appropriate. So the object, the time that it's in the air is principally based on the vertical component of the object's speed. So that's something that we're going to focus on and we have to be really careful. So the y component of v naught, which is v naught sine theta, okay, provided that the angle that's nestled between the horizontal and the vector is such. And then also we will be analyzing the x component. Okay, so that x component being v naught cosine theta. Okay, so we'll keep those two into account. But first, let's find the time t. So assuming that v naught, assuming that the initial and final height are the same, we're going to use the third basic kinematic equation. This principally tells us how long something will be in the air based on the y component. Now keep in mind that every term in the third basic kinematic equation for vertical motion represents a vertical quantity. So that's why I point out the importance of the velocity for this equation. That is the y component of velocity. Okay, so you assume these are 0, they're going to cancel. So solving for t, we'll get minus 2v naught sine theta over g. And don't worry about the minus sign. I'm assuming that because this is kinematics in 2-dimension projectile motion, that negative 9.8 will be substituted. It'll give you a positive sign. Okay, moving to the next slide. On the axis below, sketch the horizontal component v sub x and the vertical component v sub y of the velocity of the projectile as a function of time t, from t equals 0 to time t equals tp. Explicitly label the vertical intercepts with algebraic expressions. Now, I made a mistake on, especially the second graph, so got to be careful. Pay particularly close attention to the vertical axes, so vx. Now, the horizontal component of projectile velocity is a constant, unless there's air resistance, but we're going to assume that there was no air resistance. And this will show up as a horizontal line. And the y-intercept, again, it's the x component, the y-intercept of the, vx, it's the x component of the projectile's velocity. So label v naught cosine theta. Now, why not cover this concept? The area under this graph happens to be the downrange distance traveled. So that'll be the distance from the point of launch to point P. I thought that was something to noteworthy if they ask it. So the area under a velocity versus time graph will give you distance traveled. All right. Vy, when I mentioned I made the mistake, I'm just going to, full disclosure, I was thinking the vertical position as a function of time, and that is parabolic, not true for the vertical velocity as a function of time. Yes, it is changing. Its speed is changing at a constant rate. So we do have to be really careful not to mistake those two graphs. Okay, so we have our initial upward component of speed. It starts positive, and it's a maximum, at least from the beginning. And then it's going to go to the maximum height. So this is the time at which it reaches its maximum height, where the vertical speed is 0, and then it starts to make its way down. Now, I'm going to point out an interesting feature of the velocity versus time graph. Once again, the area under that graph below, and then after it reaches maximum height above the graph in the negative territory, will give you the distance traveled. And if you add these two areas, one's positive, one's negative, you should get 0 after it's reached the ground. But this will tell you how far it reaches the max height. So this would be the maximum height. And of course, because due to symmetry, we can make the argument that the amount of distance traveled up to a maximum height is the same distance vertically down. All right, next slide. All right, projectile is again launched from the same position, but the cart traveling to the right with speed v1 relative to the ground, as shown above. Projectile again leaves the cart with speed v0 relative to the cart at an angle theta above the horizontal, and the projectile lands at point Q, which is a horizontal distance d from the launching point. Express your answers in terms of v0, theta, and the physical constant as appropriate. Give a physical reason why the projectile lands at point Q, which is not as far from the launch position as point P is, and explain how the physical reason affects the flight of the projectile. Well, the horizontal motion of the cart only affects the horizontal component of the projectile velocity. And since it's rightward, the leftward component of the projectile velocity, the sum of which, it's not going to travel as far. And that's from the point of launch. So I'm imagining this cart's going to keep moving, and you could make the argument that the distance from the launch point to point P in the previous will be the same. It's just that the position of the cart will be that much further to the right as the projectile is in the air, if you know what I mean, for the amount of time that's in the air. So my answer, the downrange distance is less because the net velocity in the x direction is less. So the relative velocity is v0 plus v1, and v1 is positive to the right, and then I'm going to assume that the horizontal component of the projectile to the left is negative. So adding those together. Now the time of flight does not change since v does not affect the y component of v0. That's something you should be good to add in there, okay, in your reasoning. Okay, moving on to the next slide. Derive an expression for v1. Express your answer in terms of v0, theta, d, and the physical constants as appropriate. So I'm going to start with the downrange distance equation. So using d as your downrange distance. Usually I've taught you guys Rx. That's the horizontal range. Now, knowing that the relative velocity is the sum of the rightward and leftward component of velocities, substituting that, and then our equation from the previous work for time, and then booking those together, and then subsequently solving for v1. And you get an expression for the rightward velocity of the cart in terms of the horizontal component speed and the distance traveled for the amount of time that it's in the air. All right. Moving right along. Oh, okay. Let's just throw in kV while we're at it. In this case, minus BB. After the launch, the cart's speed is V2. Beginning at time t equals 0, the cart experiences a braking force of minus BB. And B is a positive constant with units kilograms per second, and V is the speed of the cart. Express your answers to the following in terms of M, B, V2, and physical constants as appropriate. Using Newton's law, write but do not solve a differential equation that represents the motion of the cart while it experiences the braking force. So again, they want to step you through this process of setting up a differential equation, which they may or may not ask you to solve it, but nonetheless. Okay, so some of the forces along the line of action is equal to ma, and the line of action is horizontal. I know the braking force is within the mechanism, the braking mechanism, and that could be a tangential force depending on where the calipers are. But I'm not going to get too far in the weeds with that. We're just going to assume that the overall effect is a horizontal line of action. This thing's slowing down. So minus BV to the left, there's only one force, the braking force equal MA. So this is a simpler task than in other cases where you might have an initial force to the right and then a drag force to the left. But this makes it somewhat simple. Now, since the acceleration is variable, not constant, we're going to express A as dV by dt. So there's your differential equation. Next slide. Oh my gosh! So they're gonna make us solve the differential equation. So we have to show that the speed v sub t of the cart, the velocity is a function of time of the cart is given by the equation. V is a function of time, v2 e to the minus bt over m. All right. Now, what I've done here is I've already separated the differential equation. So this is a first order, easily separable expression. So the idea is that we want to park everything that has to do with v on one side. So that'll be 1 over v dv, and then everything, most likely it's a constant, but it could incorporate some other initial values, so minus b over m dt. Taking the integral of both sides, your limits of integration are from 0 to t on time, for the time, and the limits of integration for your velocity is v naught, initial speed, to some speed later. Since the integral of the form 1 over u du, and the answer natural log of u, so evaluating the integral, and I've not that I've skipped a step, but I've done this integral a number of times, which I hope you have as well. You can go from 1 over v evaluated from v naught to v to natural log of v over v naught. So transforming log to exponential form. Let's go over that. It's worth doing. So we have minus b over mt is equal to log base e of v naught over v over v naught. So remember, you're going to take e, you're going to raise it to minus b over mt and set that equal to v over v naught. Okay, so that's what that work is. And then solve for v, which is technically v as a function of t. Okay. All right, derive an expression for the distance the cart travels from t equals 0 until the time it comes to a stop. Antiderivative. So the integral of the velocity function is the distance function. So we have v x of t is equal to integral of v2 e to the minus b over mt dt. Now, in your equation sheet on the back, you should have in your notes. Hopefully, you'll have that with you. There is the integral of e to the ax. Okay, so I'll do this for you. So integral of e to the ax dx, and that's going to give you 1 over a e to the ax. Okay, so notice that we have here the exponent is minus b over mt. If you do 1 over that, sans the x, in this case sans the t, you get minus m over v, vt. Now remember, vt is a constant that comes out of the integram before taking the integral. All right, evaluating from 0 to t, you know the drill, and solving it. And after a very long time later, let's see, go to infinity, the distance traveled from the time it the braking force is applied, that object will travel distance m over v2. Oh, right. Moving on to the next problem. All right, here we have rotational dynamics. We have a yo-yo, okay, suspended by a string. And this is the first thing that goes through my mind when I see a yo-yo. I've got tension up, mg down. The forces acting along the vertical line of action. And also knowing the fact that that tension is perpendicular to the radius of the disk. So it's going to involve both translational motion and rotational motion. All right, let's read the problem. A thin uniform disk of mass m and radius r has a string wrapped around its edge and attached to the ceiling. The bottom of the disk is at a height 3r above the floor, as shown above. The disk is released from rest, and the rotational inertia of the disk around its center is I equals 1/2 mr squared. Okay, on the circle below that represents the disk, draw and label the forces, not components, that act on the disk. Each force must be represented by a distinct arrow starting on and pointing away from the disk, beginning at the point where the force is exerted on the disk. So that what they mean by that is that show that tension applied tangential to the disk, right on the edge there, and then show mg acting on the center of mass of the disk. Okay, so there's your free body diagram. Good free body diagram, get your points. Next slide. All right, when released from rest, the disk falls and the string unwinds. The force the string exerts on the disk is F sub t, and the gravitational force exerted on the disk is F sub g. Which of the following expression correctly relates Ft and F of g as the disk falls? Now, you can default to a system of masses where M1 and M2 are hanging by a string, let's say an Atwood machine. And when the system is accelerating, the tensions in the string are less than if the system were moving at constant speed or at rest. So the tension is always less than the force of gravity if it's accelerating. If not, they're equal. Okay. And here's my justification. I added up the forces along the y-axis. T up minus mg down equals minus ma. That's if the acceleration is downward. All right, and that should be proof enough. And we're going to borrow that expression later. Express all answers in terms of m, r, and physical constants as appropriate. You guessed it. They're going to ask you to derive an expression for the acceleration a of the disk as it falls. I'm not saying you know the drill, but when you have something that's translating and rotating, folks, please apply Newton's second law and its angular equivalent, and then couple those two expressions together in terms of what those two relationships are. So as I was able to borrow my thinking in the prior slide, T equals mg minus ma. And then for the sum of the torques, we just have the one torque, the string pulling on the edge or distance away from the axis of rotation, and it's a clockwise torque, and that equals a clockwise angular acceleration, in this case, as is represented by I alpha. All right, substituting tension in the equivalent equation for Newton's second law and algebra, provided you pay attention to the minus signs. A equals 2/3 g. All right, driving expression for the change in time it takes the disk to reach the ground. We're going to use a good old basic kinematic equation for vertical motion. Object starts at rest, falls from point A to point B. So the difference in height is principally y, and solving for t, square root of 2y over g. Or there's 2y over the acceleration. In this case, the acceleration is 2/3 g. And there it is. 3 times the square root of r over g. Next slide. Driving expression for the rotational kinetic energy. Kinetic energy of rotation of the disk at the instant it reaches the ground. So applying energy, energy at state 1 is all energy at position. And then later at state 2, just before it's the ground, we have energy of rotation and energy of translation. So solving our energy expression for state 1 and state 2 for the kinetic energy of rotation, the rest is substitution. And provided that you pay attention to the minus signs, you should be good. Now, we do have to make a substitution for the speed, translational speed of the disk just before it's the ground based on its linear acceleration. So using a second basic kinematic equation to accomplish that. So we get the square root of 6ar, and that kind of whittles down our expression to a pretty simple answer, mgr, as opposed to mgh, as we've come to know in terms of the energy of position for a particle. But since it combines translational and rotational, don't be surprised if expression's got some aspect of the dimension of the disk. There it is, r. All right, next slide. Okay, oh boy, they're really putting us to the test here. A very narrow wedge is cut out of a thin uniform disk of mass m, as shown down to the right. If r is the distance from the tip of the wedge, then the linear mass density of the wedge can be expressed as follows. So I'm assuming that as you move your way out along this pie shape, the density is going to increase, and it does make sense. So, as you start slicing on your way out, you get a little more mass per unit area, or volume for that matter. So let's take that. So that's the linear mass density, how the mass is distributed along, in this case, the radial distance. Using integral calculus, derive an expression for the rotational inertia of the wedge around its tip. All right, integral calculus. Well, we're going to use the equation that specifies the rotational inertia for a continuous body. Okay, it's not enough just to look up the rotational inertia. They're going to make us derive it. All right, so here's some of our things we need to consider. We can't use the continuous body equation wholesale plug and chug. We're going to have to make some reasonable substitutions. Now, lambda is equal to m over r, which is also equal to dm over dr. Therefore, dm is equal to lambda r dr. So substituting for dm, lambda r dr. Lambda r, m over r, 25 r squared. All right, there's our substitution. And notice that we're going to get an r cubed, and the integral of r cubed is 1/4 r to the 4th. Evaluating it from 0 to r, the rotational inertia, r squared m over 100. Hope you're able to follow that. But I'd say this is the most important aspect of this problem, knowing that you're going to have to make some substitutions for dm. All right, derive an expression for the rotational inertia of the modified disk. So essentially, we're going to take the rotational inertia of the disk, which is 1/2 mr squared, and then subtract from that the piece that was removed. And again, if you fall through the algebra, you're going to get 49/100 mr squared. All right. Oh, don't panic, folks, when you see a system of masses with a couple of pulleys and a bunch of string. I've taught you guys how to determine the acceleration of A and B given slippage, but don't panic. That's not the case in this problem. All right, picture this. You see the picture, but here's the description, which pretty much follows the picture, but it's important to read the question anyway. 3 blocks are connected by strings that pass over pulleys of negligible mass. Block B is on a level horizontal surface of negligible friction. That's helpful. Block A is on top of block B. String 1 connects blocks A and B. The coefficients of static and kinetic friction between blocks A and B are mu sub S and mu sub K, respectively. Block C is hanging over the end of the table and is attached to block B by string 2 as shown above. The masses of blocks A, B, and C are m sub A, m sub B, m sub C, respectively. When block C is released, the system remains at rest. Okay. On the dot below, which represents block A, draw and label the forces, not components, that act on the block. Each force must be represented by distinct arrows starting on and pointing away from the dot. All right, so here's block A. You got a string attached to block A. Let's start with what we know. And I've labeled it TA. So there's a string attached on to the left of A, and that's pointing to the left. Now imagine block A on top, block B moving this way, and studies show force of friction always acts opposite the tendency for, in this case, block A to move. So block A is going to move to the left, therefore the friction force is to the right. Okay, that's important. Now, the force that block A exerts on block B is the weight of A, okay? And block B exerts a supporting force, a normal force. I'm just going to call F sub N A. All right. Okay, again, free body diagram is important. Get points. Next slide. On the dot below, which represents block B, draw and label the forces, not components, that act on block B. Each force must be represented by distinct arrows starting on and pointing away from the dot. All right, this is a little messy. All right, so block B. I'm showing here the tension on B acting to the left. Now, that tension is equal to the tension in A, but that's definitely a force acting on block B to the left. Speaking of strings, you have another string attached to block B. That's the string due to the hanging mass. So I'm going to show that as TC. The string on the right and on the left, the forces aren't equal, so be careful. You might, like I might say as much that this tension, it's acting on B. Well, that's going to be equal to the tension of the hanging mass, but it's not equal to this tension. It's not equal, so be really careful. Okay, so TB on the left is not equal to the tension on B to the right, so just be really careful of that. All right, the other forces. Okay, this friction force thing. Imagine, the friction force on A is to the right, but Newton's third law states that forces happen in pairs. So the force on A due to B, in terms of the friction, is to the right. And the force on B to the A, the friction is now pointing to the left. So that's that action-reaction pair. So, and that's equal, okay, in magnitude, but in this case, directed to the left. All right, now as far as the weight and the normal force, so B exerts a force of its own, mgb, and since block A is on top of block B, going to add that second vector. And then the normal force, the support that the table lends block B, which has block A on it, I'm going to consider those the normal force due to block A and B. So it'll be the sum of those weights. All right, next slide. Derive expression for the maximum value of m sub c at which the blocks will remain at rest. Okay, so we've got a coefficient of static friction for block A and B. So how much can we pull on B such that that system remains at rest? Okay, follow along. This is not easy. For me, for my thinking, I needed to draw another diagram. And if remember from the Watt-Loa days, walk along the line of action, we're going to show the vectors along the line of action, but just simply adding those up and setting equal to 0 because we have a state of rest situation here. All right, so walking along the line of action, so I'm going to move from left to right and then down and over the pulley. Minus TB, makes sense. minus F of FA. Okay, that's that friction force opposing M sub B. That's tending to move to the right. We've got TB and TA, plus TB minus TC. Tensions don't cancel, but the way I have it labeled, it does in this diagram. And then we have M sub CG equals 0. Okay. Now, knowing or owing to the fact that TA is equal to TB, that string that's wrapped around that pulley on the left-hand side, it also stands to show that TA is equal to the friction force. So I'm going to substitute TA for TA over here, and then substitute into our expression. And notice we get twice the friction force. That makes sense. And then we got M sub G equals 2 F of FA, solving for M sub C. This is the maximum mass that we can place on that hanger. All right, take a look at it, work through it a couple of times. Okay, moving right along. Okay, we're going to change the experimental setup. The setup is modified as shown in the figure to the right. Block A and one of the pulleys are removed, and block B remains on the table. There is still negligible friction between block B and the table. A lump of clay is added to block B. The students use Newton's second law to derive an equation for the acceleration A sub C of block C. Okay, the acceleration is given by the equation. Okay, that was nice of them. Okay, we know how to formulate Newton's second law, F equals ma. Okay, and therefore, if we solve for A, we get F over m in general. So, so it looks like we're going to vary, the acceleration is going to vary based on a variable force. So the relationship will be A direct proportional to F in this first part. Okay. The over M, the 1 over M part, that's going to be our constant of variation. That's my assumption here. All right. Okay. Students use the setup shown above to experimentally determine the acceleration G due to gravity in each trial. The student moves a small amount of clay from block B to block C, and releases the blocks from rest, recording the new values M sub C and M sub A. The total mass of the clay in the two blocks is 5 kilograms. The graph below shows AC as a function of MC, where M sub C is now the combined mass of block C and the mass of clay added to block C. This is a hard thing to visualize, but it's good to, in terms of explaining, when I'm thinking out loud here, explaining what's the experimental relationship or the design of the experiment based on the relationship. So A variable, F variable, okay? And the mass of the system is going to remain constant. And this is the mass of the system, okay? We're just redistributing the mass from B to A. So thus it stays constant. All right, I already drew the line of fit, that's in pink. And then I picked 2 points from the line. So that's the best line of fit. Use the best line of fit to calculate the experimental value for the acceleration G due to gravity. Well, here's my relationship. Okay, I'm picking 2 points from the line to determine the ratio of the change in acceleration to the change in mass C. Okay, and that's equal to G over the total mass of the system. Solving for G, total mass of the system, which is 5 kilograms times the slope of that line, I get 9.10 meters per second squared. Next slide. All right, if the mass of pulley in part C is significant, would the experimental value of G be greater than, less than, or equal to the value calculated in part C? Well, since you've got a pulley that's got mass, it's going to resist a change in state of rotation. So in this case, it's going to be less. Okay. a little error there. It's going to be less. You have to take that into account. All right. And just for kicks and giggles, the acceleration system, if you take the pulleys rotation inertia into account, is going to be m sub c g over mc plus mb. And I believe it's the mass of the pulley if it's a pulley rotational inertia. So we're adding the inertia to the pulley, and that's why you get a smaller acceleration. Okay, a different group of students repeats the experiment, but instead of moving the clay from block B to block C, they just remove a small amount of clay from block B and set it aside away from the setup. The equation A sub C equals m sub c g over mass total still applies to the experiment. Okay, I'm going to go back before we jump into this problem. I'm going to go back to that concept. F equals ma, and then the design experiment, we get A equals F over M. Now, in this case, the force is constant. Okay, that's going to be the constant. Okay, because the pulley, the mass of the pulley is going to remain the same, but the only thing we're going to do is we're going to take mass from the top of block B, and that's going to create the variable acceleration. So in this case, A is directly proportional to 1 over the mass, okay, because the mass is variable. So change the mass, change the acceleration. All right, so having said that, in order to provide a straight line graph that can be used to determine an experimental value of G, what two quantities should the students now graph? Well, A is a function of the inverse of the mass. Okay, let's leave it at that. So taking a look at our possibilities, look at that, first choice. Okay, that should jive with that. So that's me thinking out loud here. Okay, so I'm thinking about experimental design. I'm taking the base equation, in this case it's Newton's second law, and then looking at the dependent and independent variables and what constant of variation that may be involved here. In this case, the constant is going to be the hanging mass. Oh, right. Let me remove this here. We've got F equals ma. Okay. Yep. Yep. That's what I just said. There you have it. There were 3 problems. Wow. But a lot of really good stuff. Projectile motion, rotational dynamics, energy, KV. Gosh, it's got everything. Graph translation, data analysis, evaluating a slope of a graph, and make meaning of that. So I highly recommend reviewing this problem a couple of times. It's all good stuff. All right, take care.